Now, before completing Section 3.3, I would just like to run through a few examples where we apply the derivative rules that we just learned. So our first example is very simple. We're just going to find the derivative of f of x is equal to 3. So the first step to do this is to set up our Leibniz notation, which will look a little something like this. We have df dx is equal to ddx of 3. Now, just to reiterate, what this means is that we're taking the derivative of function f with respect to x. And to do that, we have to find the derivative of number 3. Now, lucky for us, that's really easy because of derivative rule number 1, where it states that if we take the derivative of a constant, if we have a function that is just simply equal to a constant, then that function's derivative is going to be equal to 0. So, after we differentiate f of x, we just get 0. It's as simple as that. We can also change the notation and simplify it to f prime of x is equal to 0. So again, remembering that this is Leibniz notation right here, and this is f prime of x. Both of them mean the same thing. It's just that when we're going through the steps of differentiation like we did right here, Leibniz notation is preferred. But then later, if you want to kind of simplify the way that it looks, we can use the notation f prime. Now, just to remind you what all this means graphically, here on the top I have f of x plotted, where f of x is equal to 3. Now, if I try to draw the tangent lines to this curve, which is just f of x is equal to 3, and I might have to zoom out on that a little bit, one moment. Right here, so f of x is equal to 3 would just be a flat line, which means the slopes of the tangent lines at any point on this line would be 0, as we can see right here. So although it says g of x is actually the derivative function of f of x. And again, you can see that it's just a straight line on 0. With a y value of 0. Now for our next problem, we're going to find the derivative function of f of x is equal to x squared. So as we did last time, we're going to set up the Leibniz notation to show that we are taking the derivative of f of x, which again looks a little bit something like this. I have df dx is equal to ddx of x squared. Now what's the next step? Well, now we can differentiate. And to do that, we will be using something called the power rule, which we previously discussed. Now, the power rule is one of the most common derivative rules that we're going to be seeing moving forward. And in the simplest term, the power rule is when you have x raised to a certain power, then the derivative is simply taking that power, subtracting 1 from that power. So in this case, our power is 2, x squared. So we subtract 1 from it, which would mean that we are left with x raised to the 1, and then we pull out what the power originally was, and we place it in front of x. And I have a neat little GIF that kind of shows us how that looks. So take a look down here in the right-hand corner. So right now, we have x squared. We pull n in front, and then the power becomes n minus 1. And so for our example, f of x equals x squared, if we take the derivative, we have 2x. That's because we had x raised to the second power, x squared, and then the derivative of that is x raised to the 2 minus 1, which is just x raised to the first power, which is just x. And then that squared, that 2, we multiply, we pull it out in front, and we multiply it by x. And once again, we can rewrite it as f prime is equal to 2x. Now, the next example looks very similar to the one that we had before. However, the only difference is that now we have a 2. We have a constant. We have the constant 2 multiplied by x squared. So how do we differentiate this? Well, it's actually quite simple. First, we need to set up our Leibniz notation, like always. and we have df dx is equal to ddx of 2x squared. Now, what we can do in this case is simply take the 2, that constant that is being multiplied by x squared, we take that 2 and we pull it out in front of ddx, so it can just kind of rest there until we do what we need to do to x squared. And then finally, when we differentiate, we're going to end up in 4x. That's because now we're using both the constant multiple rule and the power rule. So again, we had our x squared, and we pulled we had 2x squared, and the 2 went down in front here to be multiplied by 2, which means that we have 4x remaining. Plain and simple. It's basically, this problem was just the power rule with an extra step. So in short, if you have a constant right here in front, you can, one moment. If you have a constant out here in front, you can kind of just pull it out in front and do the differentiation to your x term, and then worry about it later towards the end. And then again, we can rewrite it as f prime of x is equal to 4x. So it's just like the previous example, except with one extra step. Now this next example is f of x is equal to x squared plus 3. We're going to find the derivative of that, and we're going to be using pretty much the same exact steps as we did in the first and second problem, because we're dealing with both x squared, which we did in the second problem, and 3, which we did in the first problem. The only difference is that now we're dealing with both terms. So, first things we need to do is set up our Leibniz notation. Now, because we have two terms added together, we're going to use a derivative rule called the sum and difference rule, which is right over here. And it just basically is saying that if you have two terms that are added together, like x squared and 3, for example, you can simply take the derivative of both of those expressions individually. So again, setting up our Leibniz notation, now it simply look a little something like this, and then we just basically follow the same exact steps that we did in the first and second problem. We're going to need to use the derivative of a constant function rule and the power rule. And I'm not going to go into too much depth about that because we already covered that in previous problems. Which would give us simply 2x, because the expression d dx of 3 is just going to be equal to 0. And the derivative of x squared, as we covered in the second example, is just 2x. So we're left with df dx is equal to 2x. And if you're wondering why the derivative of a constant is just 0, here's a good example. On the top graph, I plotted x squared. And take a look at the bottom. The bottom plot is the derivative function. It maps out the slopes of all of these tangent lines. And if you recall, the derivative function of x squared is 2x. Now look what happens when I add plus 3 to x squared. Our original function f of x, it shifts upward by 3. It shifts upward in the y direction by 3. But take a look at our derivative function. It doesn't move at all. It stays exactly the same. That's because the slopes of these tangent lines are completely independent of where that vertex lies. They're completely independent of how far up and how far down this function is shifted. So if I go to the vertex, which is right here at this point, I see that I have a tangent line slope of 0. And that tangent line slope of 0 occurs at x equals 0, whether or not the function x squared is just x squared or x squared plus 3. So in short, that's why constants, the derivatives of constants are 0, because it doesn't matter how far this function on top gets shifted up or down, the tangents to the curve are all going to have the same slope. Now our final example is going to be slightly more labor intensive. We are going to be finding the derivative of f of x is equal to x plus 3 times x plus 2. And to do this, we are going to be using something called the product rule that we see down here on the right-hand side. So it says d dx of u times v. Now, what does u times v mean? Well, anytime we have two terms like these multiplied together in a function, we're going to treat them independently. We're going to treat them each as its own independent function. And we can choose which one is going to be u and which one is going to be v. So I'm going to say that this first term right here is going to be u. So x plus 3 is equal to u. And this second term is going to be v. All right. And knowing that, what we have to do is we have to first find the derivative of v, of function v, and also the derivative of u as well. So what does that look like? Well, we already said that v is equal to x plus 2, and that u is equal to x plus 3. The derivative of u is just 1, and the derivative of v is also just 1. That is because if we look into the functions u and v, we can use the summation rule. And if we take the derivative of x, that is just going to be equal to 1. Because again, we have the power rule being applied. And then in u and v, we also have the numbers 2 and 3, which are just constants, and those go away. Those can just become zeros, as we discussed before. All right, well, now that we have the derivatives of u and v, what is the next step? Now we can apply the product rule. We can apply this rule right here. So we need to multiply u times dv dx plus v times du dx. So we're going to be first multiplying this expression right here by this one, and then adding that to the product of this expression and this one right here. And here's a little animated GIF in the corner as well of what that looks like. Now, I know it doesn't say u and v, but it's basically saying the same thing. If this visual right over here helps you more, then great. Just remember that f of x and g of x correspond with u and v. All right, well, now we have our product rule equation set up, so let's plug in all the numbers. And, well, it was, since f of x in this case is a relatively simple function, then the derivative of f with respect to x after we use the product rule here is just going to be x plus 3 plus x plus 2 instead of times x plus 2. And of course, if we expand that and simplify it down further, we get the derivative of f. The derivative of f of x is just equal to 2x plus 5. And again, we can use our f prime of x equals 2x plus 5 notation as well. And that wraps up section 3.3 for us. Thank you.